Hey everyone, and welcome. If you've ever written a line of C# code, hit that run button and just kind of wondered, what actually happens now? Well, you're in exactly the right place. Today we're going to pop the hood and really demystify that whole journey your code takes from just being text on a screen to a full-blown running application. So let's fire up the engine and see how this thing works. You know, it all boils down to this one simple question. You spend all this time typing out your classes, your methods, your variables, and then you're done. But then what? There's this whole invisible assembly line that kicks into gear. And honestly, understanding that process is one of the biggest keys to really mastering C#.
All right, so before we can see how the machine gets built, we first have to understand the tools, right? And that starts with the two most fundamental pieces of the puzzle, the C# language itself and the .NET framework that it lives in. So here's the most important distinction you gotta get. C# is the language. It's the set of rules, the grammar, the syntax you use to write instructions. Think of it like a super detailed blueprint for a car. .NET, on the other hand, is the framework. That's the factory with all the machinery and the workers that takes your blueprint and actually builds the car. See? You can't have one without the other if you want a car at the end.
Okay, so we've got our blueprint. Now, how does the factory actually read it? Because here's the thing, your computer's processor has no idea what C# is. It needs a translation. And this happens through a pretty cool multi-step process. Let's trace that journey from start to finish.
So, this whole journey really breaks down into three big steps. First, you've got your C# code, the stuff you and I can read. That gets compiled, but not directly into machine code. Nope. It gets turned into something called intermediate language, or IL for short. And then only at the very last second, right when you run the program, that IL gets translated into the native machine code that your processor can finally understand.
So what's the deal with this intermediate language? The absolute best way to think about it is like a universal flat-pack furniture kit from IKEA, right? It's not a finished table yet, but it's got all the standardized parts and instructions ready to go. And this is awesome because it means you can ship that same kit of IL code to a Windows machine, a Mac, or a Linux box, and each one knows how to assemble it on site.
So who's doing the final assembly? Who takes that flat-pack furniture kit and turns it into a table? Well, that's the job of the just-in-time compiler, or the JIT compiler. It's like the on-site mechanic. It takes that IL code and, right as it's needed, assembles it into the final machine code that is perfectly optimized for the room it's in, whether that's an Intel chip or an ARM processor. So, why bother with this extra step? Why not just compile it directly? Well, the payoff is this incredible flexibility. It means you can write and compile your code on your Windows laptop, and then you can take that same compiled code and run it on a totally different Linux server. The JIT compiler on that server will make sure it generates the absolute best, most optimized machine code for that specific environment. It's a game changer.
Okay, but something has to manage this entire factory floor, right? It has to oversee the JIT compiler, the code, the memory, the whole shebang. That something is the engine at the very heart of .NET, and it's known as the Common Language Runtime, or CLR.
The CLR is basically the master control system. It's the execution environment where your code actually lives and breathes while it's running. And any code that runs under the watchful eye of the CLR gets a special name. We call it managed code, precisely because the CLR is managing every single aspect of its life.
And believe me, the CLR is a very busy manager. It's got a ton of critical jobs on its plate. It's the CLR that actually tells the JIT compiler, hey, time to get to work. It's also in charge of all the memory, allocating it, and importantly, cleaning it up, which we'll talk about in a sec. And it acts like a security guard, enforcing rules to make sure a string doesn't suddenly pretend to be an integer, which helps prevent a ton of bugs.
All right, let's zoom in on what is maybe the CLR's most famous and honestly most helpful feature, the way it automatically manages memory for you. This one thing saves developers from a whole world of pain. So when we talk about memory, we're really talking about two main places, the stack and the heap. The stack is super organized, really fast, and it basically cleans itself. It's perfect for simple things like numbers or booleans. But the heap, well, the heap is where all your complex objects and strings live. It's much more flexible, but it can get really messy really fast. And if you're not careful, you can leave old, unused objects lying around, wasting space. And that's where our housekeeper comes in. Meet the garbage collector, or GC. Think of it as a little robotic vacuum cleaner that's always running in the background. It periodically sweeps through the heap, finds all the objects that your application isn't using anymore, and automatically cleans them up, freeing that memory.
It just keeps things tidy so you don't have to worry about it.
So this sounds amazing, right? A system that just cleans up after itself automatically. What could be better? But here comes a classic, and I mean classic, interview question. Does it handle absolutely everything?
And the answer, which is so important to know, is a big no. The garbage collector is really powerful, but it has limits. Its power only extends to managed resources. Those are the .NET objects created and living inside the world of the CLR. If your code uses what we call unmanaged resources, things like a direct file handle or a database connection or a graphics object, the GC can't touch them. It doesn't know what they are. You are responsible for cleaning those up yourself.
So we've seen the engine. We know how it runs. Now, how does knowing all of this change the way we actually design the car? Well, it directly affects our architectural choices, right back at the blueprint level, especially when we're dealing with core programming principles like abstraction.
So let's look at a classic architectural choice that comes up all the time: abstract class versus an interface. An abstract class is kind of like a partially built car frame. It's a parent class that provides some of the implementation, some common logic, that its child classes can then inherit and build upon. An interface, though, is a pure contract. It's a blueprint with zero implementation. It just makes a promise. It guarantees that any class that uses it will have a certain set of capabilities. And here's the key difference. A class can only inherit from one abstract class, but it can implement as many interfaces as it wants.
So there you have it. We've gone on this whole journey from the simple blueprint all the way down to the factory floor, and we've seen the engine that powers the whole thing. The real takeaway here is that knowing how it all works under the hood empowers you to make much better decisions about what you build. You get the runtime now. So the only question left is, how are you going to use that knowledge to design truly elegant, efficient, and rock-solid applications? Because that, right there, is where the next level of mastery begins.